All right, we're going to start looking at prime numbers. And prime numbers are a topic, a special type of number that have really intrigued people for thousands of years. There's lots of study about prime numbers going way back in history. People have always looked for patterns with prime numbers. And in modern day times, prime numbers are a big part of a lot of complicated algorithms. Most famously, they're used in encryption. And there are prime numbers that are, enormous in size. In fact, a Google search for the largest prime number tells us that on January 25th, the number 2 to the 57,885,161 minus 1, which is a special type of prime, a Mersenne prime, right, has over 17 million digits. Okay? And there's constantly people out there running computer code trying to find the next largest prime number. There are some applications for this that we'll maybe touch on in this course. The book spends a little bit of time on RSA encryption and modular exponentiation. Those are not things we're going to get into as far as testing or quizzing, but they might make for an interesting read and things you might revisit down the road. Now, let's just do a quick review of what prime numbers are. A prime number is a number greater than 1. 1 does not count as a prime number, whose only factors are 1 in itself. So the first prime number is 2, then we have 3, then we have 5, 7, 11, 13, 17. The next one would be 19, and so on. And basically, the only way you can determine whether or not a number is a prime number is to start seeing if all the numbers less than the square root of it go into it. Once you've reached the square root of the number, you would have gotten the other factor on the other side. So basically, if somebody gives you a number and asks you if it's prime, you have to ask yourself, is it divisible by 2? Is it divisible by 3? Is it divisible by 5? And so on, over and over again. And that's why it's good for encryption, because it takes a long time to figure out whether or not a number is prime and how to break that number down into its components if it's not. Now, the fundamental theorem of arithmetic tells us that every number greater than 1 can be written either as a prime itself or a product of 2 or more primes. And this is something you probably did a long time ago, is to take a number and break it down into its prime factorization. Now, we're going to use this as one technique to find GCDs and LCMs. GCDs and LCMs are used in fraction arithmetic and for other applications as well. So let's think about the number 180. We're going to start at the beginning of this prime list, and we're going to see if we can break the number 180 down. Is it divisible by 2? We know, in fact, that it is. It's 2 times 90. And this is sometimes called a factor tree. Right? 90 is divisible by 2. That becomes 2 times 45. Now, there are certain tricks or techniques for determining divisibility. Anything that ends in an even digit is divisible by 2. There is a technique for 3. If you add the digits up, like this 1 plus 8 plus 0, right, that adds up to 9. That number 9 is divisible by 3, so that means the number itself is divisible by 3. Now, you might also know that 45 is divisible by 3. Right? It's 3 and 15. 15, again, can be broken down into 3 and 5. And this gives us the prime factorization that 180 would really be 2 squared times 3 squared times 5. And having this prime factorization can help us do other things like the greatest common divisor, least common multiple, that we'll be looking at next. Okay? The fundamental theorem of arithmetic just guarantees that we can do this for any number. Okay? So GCD of A and B, it's the greatest common divisor, right? It's the largest integer that evenly divides both A and B. Okay? Now, the GCD is usually smaller than the two numbers. It could be actually one of the numbers if one divides the other. A lot of times people get the LCM and the GCD mixed up. Sometimes we think about the greatest common factor as well. This is greatest common divisor. It's the same basic idea. So if you look at 12 and 42, right, if you were to break 12 down into its prime factorization, it would be 2 squared times 3. This would be 2 times 3 times 7. And if you were to look at the overlap here, what do they have in common? They each have a 2, and they each have a 3, and that's the 2 times 3 that makes up the 6 here. This is the basic algorithm we're going to use to find GCDs. Okay? The LCM is a multiple. Multiples are bigger, generally speaking, than both numbers, although, again, if B happens to be a multiple of A, then one of these numbers could be the least common multiple. But least common multiple, you're not looking for something that goes into them. You're looking for something that they both divide evenly into. So you're looking for the smallest integer that's divisible by both a and b. So with 12 and 42 again, what we can do is we can actually use the prime factorization here as well. 2 squared times 3, 2 times 3 times 7. When you look at the 2's, right, this one's going to need 2 2's. This one's only going to need 1 2. Right? But in order to cover both of these numbers, you're going to have a 2 squared. Right? Then when you look at the 3's, right, they each have a 3, so you're going to need a 3. And then the second number, 42, actually has a factor of 7, so you're going to need a 7. And if you multiply this out, you get 12 times 7, or 84. Right? So what you're looking for with the GCD is basically the overlap, or if we want to go back to set terminology, sort of the intersection. And in the least common multiple, we want to sort of put them together, take the largest exponents, not the smallest. Here we can think about taking the smallest exponents, right, up here. Now we want to take the largest exponents of all these and put them together, sort of like the union. Okay? So let's try this. Now for certain numbers, small numbers, you might have been able to come up with the 6 here by looking at the 12 and the 42. But if you're not seeing the answer, then you can break this down into the prime factorization. Now if you happen to recognize that 60 is 12 times 5 and 84 we just found out was 12 times 7, it might be clear that the GCD of 60 and 84 is 12, right? But in order to find the LCM, we're going to have to do some work anyway. So let's break 60 down into its prime factorization. We know that it's going to be 4 times 15, so it's going to be 2 squared times 3 times 5. And if we break 84 down, luckily we just did that, 2 squared times 3 times 7. Okay, so hopefully here you can see for the GCD, we're going to take what's common, the 2 squared and the 3, that's the 12. Right? But for the LCM, we're going to have to take the max. So we're going to take the 2 squared, we're going to take the 3, this one needs a 5, and this one needs a 7. And when you put that all together, right, you've got 2 squared times 3 times 5 times 7. This is really, we already know that's 12 times 35. Right? That's 350. It's going to be 420. It's all said and done. Right? So you can use the prime factorization to do the GCD and LCM if you want. Now this one I already gave you the prime factorization because that would be once the numbers get big, that becomes a really tedious process. Okay, so I'm just going to call these numbers A and B to save myself the copying here. What's the GCD of these two numbers? Okay, for the GCD, we want to see what they have in common. This one has 3 factors of 2. This one has 5. Right? I don't have 5 sitting over here in the 3, but I do have 3 sitting in the 5. So I'm going to take the 2 cubed, the 3 squared, and over here they don't have any 3's in common, so that's not going to count. The 5's, I've got 4 of them here and 2 of them here, but I only have 2 in common. So I'm going to take the 5 squared. This one has a 7, but this one doesn't. B has an 11, A doesn't. So this would be it for the GCD. Now in a case like this, you probably could multiply out 8 times 25. And get 225 as the GCD. But once the numbers start getting really big, just leaving them multiplied, factored like this would be enough. I'm going to assume at this point in your math career, you could multiply that out if you need to. Now for the LCM, we've got sort of a different scenario, sort of the reverse to go here. Right? In order to cover this number, A, I only need 3 factors of 2. But if I'm going to also cover B, I need 5 factors of 2. So I better start with the 5 factors of 2. 5 is certainly enough for 3, but 3 is not enough for 5. Right? So we're basically going with the largest exponent. I don't need any 3's for B, but I need 2 of them for A. So I have to include the 2 factors of 3 to cover A. I'm going to need 5 factors of 4 factors of 5, sorry, for A. Only 2 for B, but I've got to go with the largest one, 5 to the 4th. And then I need 1 7 for A, even though I don't need it for B, and I need 11 cubed for B, even though I don't need it for A. Now there's no point in really trying to calculate this and figure out what that actual number is. Okay, so when you're finding the GCD and LCM, sometimes you can just stare at the numbers and the answer pops into your mind because you've worked with these numbers before, but you can always resort to breaking it down to the prime factorization. It's a little bit tedious, But certainly on quizzes or tests, you'd be either given small enough numbers that it's manageable, or you'd already been given the prime factorization. It's just a matter of picking the right things. Now, this is a very nice but tedious procedure. It's sort of obvious, but it takes a while to do. We're going to discuss in the next video the Euclidean algorithm. The Euclidean algorithm seems a little bit strange. It's going to use modular arithmetic, but it's going to and the division algorithm, but it's going to very quickly get to the right answer without us having to do so much work in calculation. So that'll be in the next video. Make sure you can practice this using prime factorization.